Welcome to lesson 9 in our unit here, and today we're going to be talking about friction. And so I'll try to draw a little diagram. Let's say if we had a block of wood that's on a surface. So I'll try to draw this block here. And okay, there's one example of the block. And let's say that right now that's a large surface that's on there, like a large face, I guess I could say. And then we kind of put it upright and put it on another surface here like this. So I don't know if you can tell if those are the same. This would be a large surface that's sliding along, and this would be a smaller surface. It turns out if I was to slide those both at constant velocity, so I'd have an applied force here and a friction force there, and if I did the same thing for both of them, it turns out that actually the friction force would be about the same. So it does not actually depend on this one here. It doesn't depend on the amount of surface area that is being in contact, which is a little bit different than we would have thought. I think a lot of people would say, hey, wouldn't I get more friction where the face of the block that has more surface compared to the one with less surface? And no, that's not the case. The only thing that friction depends upon is, first of all, the type of materials that are in contact. So in this case, if it's a wooden block and say a wooden table, wood on wood, or if I was to sand down the wood, I would be changing the type of materials that would lower the friction. Another thing about type of materials, if I added some oil, to make it more slippery, that would change the type of materials. But if I'm using like, say rough oak versus a laminated countertop, that would be the example of type of materials in contact. The other one is the normal force exerted by one object on the other. So if I was to finish the diagram here, there's also there's a force of gravity downwards. Let's see if I can grab a pen here. There's a force of gravity downwards, and there's a normal force upwards. So even though when I draw the free body diagram, the force goes away from the object, but really what's happening here, it's this interaction between the surface and the object, where the surface is pushing back up on the object, and it's that pushing back up on the object which changes the friction. Okay, so the formula is a rather simple one. Here it is. The force of friction is equal to, now here's a new symbol for us. This is a Greek letter. That Greek letter is this one here. If you spell it out, it's mu. We pronounce mu like the sound a cat makes, and it's the same prefix as in metric for micro, which means a millionth. And in this formula, it has no units. So you'll notice that the force of friction is a force, so it's in newtons. The normal force is a force, so it's in newtons. But here, no newtons, or no units at all. And I'll just make one comment about this this formula in general. It's not a great formula, in that sometimes you'll get in the real world that this is sort of loosely fits. Okay, so not always a great predictor, maybe I'll put it, of real world. Okay, so if you look at F net equals ma, that's bang on. That's always going to be true. If you take a look at Fg is equal to m times g, take these ones to the bank, 100%. The force of friction, it's kind of loosely based on observation, and it's a pattern, but it's not necessarily grounded in according to physics, this is the way friction works. Okay. All right, so when I'm talking about this mu, this coefficient of friction, and the two different surfaces, here's some examples. If I have, I don't know, well, here's a good example: rubber on concrete dry, and the coefficient of kinetic friction. So static friction versus kinetic friction. Kinetic means moving, and here static friction would be not moving. So moving, or I could say sliding. So what would this be an example of rubber on concrete? Well, if I had a car that you would lock the brakes, right? So it's skidding. And if it is on dry concrete, then look how big that coefficient is, like compared to some of the other ones. It really does a good job of supplying a lot of friction. So we are able to slow down our cars rather quickly. If it's on rubber on wet concrete, you're going to find that there will be not as quite as large of a coefficient of kinetic friction. Thus, we won't be able to slow down quite as quickly if the concrete is wet using our car. All right, there's some couple paragraphs here about static friction versus kinetic friction. I don't do too many examples of this, so don't worry too much about this. But if you are interested, one that would be an example here is if I had an object here and I'm trying to push it and I'm not giving it enough force to start it from moving. All right, so this is where I would say that the force of friction is going to be less than or equal to the static coefficient times the normal force. Like if I'm only pushing, I'll put my applied force this way. If I'm only pushing with 10 newtons of force, clearly the force of friction is only going to be equal to 10. As I push harder, I might increase this to 20, in which case the force of friction is going to be 20. At no point is the force of friction going to be more than this applied force, because it's not going to cause it to accelerate leftward unless it's actually moving to the right. Now, at some point, though, my applied force is going to be greater than the force of friction. Let's say if I get to 30, and the force of friction can't go any higher, then it's going to start to accelerate to the right. And then we're no longer talking about the static friction, then we're talking about the kinetic friction. And check it out. What's a pattern that you see here? If I compare this static friction versus kinetic friction, the kinetic friction is a little bit lower. So, and I think this is, you're sort of familiar with this in real life. If I've got a box and I have to, push it enough to get it started to move, I'm going to have to overcome that static friction to begin with. But then, once it's already moving, it doesn't take as much force to keep it going at a constant acceleration, which tells me that the kinetic coefficient is less than the static coefficient. Okay, well, let's do a few examples here. I've got 3 examples, and to be honest with you, only the first 2 are ones that we're ready for at this level. The third one I'm going to start for you, but I'm going to make it a little challenge. I don't know, maybe I'll give you a little sticker or something if you can finish 3 on your own, and then your homework will be the practice questions following that. So let's look at the first one. And for each one of these ones, we're going to be drawing a free body diagram. We've got a few formulas up our sleeve. We've got the Fg equals mg, we've got Fnet equals ma, and we have our brand new formula. The force of friction is equal to mu times the normal force. I'm not going to worry about the difference kinetic and static. I'm just going to use a formula like that. Okay, so number 1 is a horizontal force of 50 newtons is required to pull an 8 kilogram block of aluminum or aluminium at a uniform velocity across a horizontal wooden desk. So let's try to draw that. Okay, so what are all the forces? Well, let's say that the applied force here is to the right. We can really pick which direction, and that we are told is 50 newtons. When you see the words a uniform velocity, alarm bells should be going off right now, and this is nice to see because that means that the forces are going to be balanced. Okay, forces balance. In other words, the only other horizontal force we have here is friction. So this friction, we are told, is 50 newtons, just because of the combination of this 50 newtons and the forces are balanced, and that there are no other horizontal forces. Of course, there's also the force of gravity, and there's the normal force. So it says, what is the coefficient of kinetic friction? In other words, the question they're asking is, what is mu? What's that symbol going to be? Well, if I take my new formula and I say, hey, I need to solve for mu. So if I rearrange this, I'd have to divide both sides by the normal force. So once I've done that, it's going to look like this. So what I need to do is find out the friction force. Hey, I know that, it's 50. And then I need to divide by the normal force. Oh, what's the normal force? Well, looking at the normal force, these two are going to be equal. In fact, I'll put these marks in there too. The normal force is going to be the same thing as the force of gravity. But what is the force of gravity? Well, it's m times g. So this is going to be equal to 8 kilograms. And let's use 9.8 on this sheet, okay? Let's say g is going to be equal to 9.8. I'll take the math a little bit more seriously on this one. So 8 times 9.8, and if I do my math, what is that, 78.4 newtons. So I can go and say that's going to be the same thing as my normal force, 78.4. Put it down here, 78.4, and we are ready for the answer here. We will get 0.64. And it feels funny not to put units after that, but there are no units for the coefficient. Okay, we'll try number 2 here. It says the driver of a 2,000 kilogram car. You know what? Let's put a dot there and say that there are 1, 2, 3, 4 significant figures here. Okay, even though the question didn't have it, let's just say it so that we know where to round our answer. And then here is the answer, and then we'll have 1, 2, 3, 4. We'll have 1.1990 newtons will be our answer, just to have somewhere to round it off. But let's confirm that that is the right answer. Okay, it says calculate the force of friction. Well, let's draw our free body diagram. So, applies the brakes on a dry concrete roadway. So, let's say it's been moving to the right, and now they apply the brakes, so there's going to be a force of friction to the left. And of course, there is a force of gravity, and there is a normal force. The force of gravity is going to be equal to 2,000 times 9.8, that's our mass, times our g, which is 19,600 newtons. The normal force will be that exact same amount. And so our force of friction is going to be equal to mu times the normal force. What is the mu? And it tells us, use the table on the previous side. Okay, brakes on dry concrete roadway. Alright, so if I pop up there, that's the one we were looking at before. I think that your car, the tires are made out of rubber, so we do want this one. We want 1.02. Okay, so we'll just say here from the chart mu equals 1.02, and then we'll plug it in here. 1.02 multiplied by 19,600. And I think that's where we get our answer. 19992. And if we're going to do 4 significant digits, we'll say 19990 newtons, where those ones are the ones we know. There's our answer. Okay, I hope you're getting the hang of this. I'm going to do this last one, but I'm going to just tell you this one is really a next unit question. It has no business being in our example questions, so don't worry, you're not going to get questions this hard. A 20 kilogram box. Okay, so we would have a force of gravity downwards of 20 times 9.8, which is what, 196. Okay, and now I have an applied force that is at an angle, that's being pulled up at an angle. The force is applied at an angle of 40 degrees above the horizontal. Okay, so what we're actually going to do is we're going to take this applied force, and this is what next unit is about. So you're getting a bit of a preview. This is 100 newtons, and we're going to pretend that it is actually a horizontal one. Here, I think I'll use a different color for this just to highlight. We're going to pretend it's a horizontal, and I'm going to call that one FAX because it's in the X direction, and an FAY. These are what we call components. And so we're going to replace in our diagram. I'm going to take out this one. I'm going to replace it with these two because these two are equivalent to the same thing. Well, trig is very helpful here. We're going to have to figure out what FAX is and FAY are. So the cos of 40 degrees is equal to the adjacent over the hypotenuse. The adjacent is FAX and the hypotenuse is 100. And the sine of 40 degrees is equal to the opposite over the hypotenuse. So we can figure these out, can't we? We'd say FAX is equal to 100 times the cos of 40 degrees, and FAY is going to be 100 times the sine of 40 degrees. Okay, so that's cool. And then what we're going to do is, if I can make some space here, I'm going to redraw this diagram. So here's my box again, and then I'll say, okay, here's my FG equals 196. Instead of FA, I'm going to write an FAX and an FAY. And I think I'm still going to have a normal force, probably. And I will have a force of friction here. Okay. Now I'm going to stop here. I'm going to say, see if you can finish this on your own, but I'm just going to point out that what will be the acceleration in the y direction? Well, what's going on here? There's a box being dragged along the floor. Will it accelerate at all vertically? I think the answer is no. What would be the net force of all the y directions? I think the answer is 0, because it's not accelerating that direction. Use that information to find the normal force. Okay? Use that information to figure out the normal force. This, these, I'm trying to find a highlighter. These three forces have to add up to 0. So if you do a little math, you can figure out FAY, and then you do a little more math, you can figure out the normal force. And then you can slowly figure out all the answers for that one. Okay, so that's kind of a little bit of an advanced question. In a couple weeks, you'll be able to do that without even, losing any sleep. And so your homework now is, I think, is it on the next page? Let me just check. Yeah, so you have a homework, these practice questions, and draw free body diagrams, and the answers are actually there shown for you. And then after that, you've got this short little worksheet here to do as well. So good, and I'll see you in class.